Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here. Today we're taking on a topic that honestly often strikes total fear into the hearts of calculus students. We are talking about optimization. But don't worry, seriously, we're going to completely demystify this whole thing today. We're going to strip away all the confusion and look at the exact bulletproof algorithm you need to solve literally any optimization problem without falling into those notorious mathematical traps.
Okay, let's dive right into this. I want you to just picture a dog playing on the beach. You throw a frisbee out into the water. Does your dog instinctively know how to calculate the absolute optimal path? Combining running on the sand and swimming in the water to reach that frisbee in the minimum amount of time? Or think about the beverage industry for a second. How did these huge companies design the perfectly proportioned can to minimize the amount of aluminum they use, while still holding exactly 355 cubic centimeters of liquid? Well, these aren't just fun riddles. They're actually optimization problems hiding in plain sight. So here's our exact mental roadmap for today's explainer. We're going to start with the art of optimization, walk through our strict algorithm, look at the power of constraint equations, uncover the domain boundary trap, go over some frequent computational errors, and finally do some practice with our frisbee and the can. All right, first up, the art of mathematical optimization. At its core, mathematical optimization is really just about finding the absolute best, most efficient way to carry out a specific task. Whether you're an engineer trying to maximize the strength of a beam, an economist trying to minimize costs, or, just trying to find the highest point on a curve, you're optimizing. Imagine you need to construct this massive cylindrical water tank you're seeing here. It has to hold a very specific volume of water, but sheet metal is super expensive. So your goal, your optimization challenge, is to find the exact dimensions, the specific radius and height that will minimize the surface area, and therefore the cost, while still holding that required volume. How do we do that without just randomly guessing? Well, we need a blueprint. Which brings us to part 2, the strict problem-solving algorithm. I literally cannot stress this enough. Skipping steps in this strict sequence is exactly how marks are lost on exams. You absolutely need a systematic approach. So here is your foolproof algorithm. Step 1. Always draw the scenario and label your variables. Never skip this. Step 2, identify your objective function. This is the actual thing you want to maximize or minimize. Step 3, find your constraint equations. Think of these as the rules of the game. And finally, step 4, use those constraints to reduce your objective function down to just one single independent variable. Let's look a bit closer at those middle 2 steps, because they are the real engines of this entire process. So, section 3, the sheer power of constraint equations. So the crucial point here is really understanding the difference between what we want to achieve and what we're forced to work with. First, we have the objective function. This is your ultimate goal. If you're building a can, your objective function is the formula for surface area, which you obviously want to be as small as possible. If you're the dog running after that frisbee, your objective function is the total time it takes to reach the target. But you can't just make a soda can 0 inches tall to save metal, right? It has to actually hold a specific amount of liquid. And that is your constraint. It's a strict condition, like a fixed volume of 355 cubic centimeters, or maybe a set amount of fencing that restricts your possible solutions. The constraint is basically the mathematical glue that links all your variables together. And what we're looking at here brilliantly illustrates how this all works together. On the left side, we have an objective function for the volume of a box with a square base. V equals W squared times H. Now that has 2 variables, width and height. It's way too complex to optimize directly. But we have a constraint. Let's say the airline policy says the combined length and girth, 2W plus H, cannot exceed 64. By solving that constraint for H and plugging it back into our volume formula, we completely transform a multivariable nightmare into this beautiful single curve on the right that we can easily analyze using calculus. All right, on to section 4, and pay attention, because this is the domain boundary trap. Okay, so once we have that nice curve and we take the derivative to find the peak, we're done, right? Actually, no, not always. This right here is the emotional climax of our mathematical journey, and it's where so many students get their hearts broken on test day. Look at the graph of this polynomial function. Say we want to find the maximum value on the interval between x equals 2 and x equals 7. Notice that local maximum on the left, where the derivative is 0. A lot of people find that critical point and just declare victory. But look at the right side. The absolute highest point on this entire graph isn't where the derivative is 0. It's actually right at the harsh edge of the interval at x equals 7. This is exactly why you must absolutely always check the endpoints of your domain. Let's clearly contrast these two things.
A local extremum is found at critical points. That's where the derivative is either 0 or undefined. That's just a local dip or hill. But the absolute extremum, the true global maximum or minimum for your specific problem, often hides right at the edges. Finding the critical point is literally only half the battle. You have to take those critical points and the endpoints of your defined domain and plug them all back into your original objective function to see which one actually yields the greatest or smallest value.
Moving on to Section 5, Frequent Computational Errors.
Beyond forgetting to check those sneaky endpoints, what else goes wrong when the pressure of an exam really hits? Well, let's arm you against the most frequent point-losing traps. First, forgetting the chain rule entirely. If you're optimizing a function with a square root or something raised to a power, and the inside isn't just a plain x, you absolutely must multiply by the derivative of the inside. Second, misusing the product rule when you have two functions multiplying each other. Third, like we just talked about, skipping those domain endpoints. And finally, careless algebra slips. Expanding a plus b squared and forgetting the 2ab middle term literally ruins your entire calculus derivation before it even really begins. Remember, most of these mistakes happen because students blindly apply a rule without checking if the mathematical conditions are actually met. Just slow down and verify your steps.
And finally, Section 6. Let's put this into practice with our Frisbee and the can.
All right, let's apply our bulletproof algorithm to those real-world problems we hooked you with at the very beginning. First, the dog and the Frisbee. We want to minimize total time. And time equals distance divided by speed. Now, the dog runs way faster on land than it swims in the water. So by setting up an objective function for total time based on an angle theta where the dog jumps into the water, we can take the derivative. And guess what? We find that dogs actually do choose the precise critical angle that minimizes this complex mathematical function. They instinctively combine running the arc and swimming the chord to fetch that Frisbee in the absolute minimum time. They're like natural optimizers.
And what about our soda can problem? Well, we used the fixed volume constraint of 355 cubic centimeters to eliminate the height variable. Then we took the derivative of the surface area function, set it to 0, and solved for the radius. The mathematical result, 3.837 centimeters, is the optimal radius to minimize the aluminum used. But here's a bit of fun reality for you. If you measure a real soda can, it doesn't quite match these mathematically perfect dimensions. Because, real-world constraints like shelf stacking, ergonomics for holding the can, and vending machine mechanics actually change the objective function that beverage companies have to use in the real world. And that brings us to the end of our explainer today. We've mastered the strict algorithm, we've tackled constraints to reduce variables, and we've learned to avoid the trap of ignoring our endpoints. So I'll leave you with this provocative thought. If a dog playing on a beach instinctively knows how to optimize its path to find an absolute minimum, where else are absolute extrema hiding in plain sight in your daily life? Look around. Mathematics is quite literally everywhere, constantly optimizing the world we live in. Thanks for learning with me today, and keep exploring.